Kia ora everyone, thank you for coming. So it's a great pleasure to run fresh off the ice again. It's always a highlight of the Antarctic Society calendar. And it's my pleasure to introduce our first speaker, Denise Fernandez, who is a physical oceanographer working at NIWA. And she has just come off, really, co-leading a voyage of the TANGAROA into the Ross Sea, which is what she'll be talking to us tonight about. And Denise is also one of the co-PIs on one of the main core programs into the next phase of the Antarctic Science Platform.
Well, thank you. Good evening, everyone. It's my pleasure today to be here and presenting our experience going to the Ross Sea with my co-voyage lead, Craig Stevens, which is present in the room. TANGAROA research vessel is going to the Ross Sea every 2 years. And this year, 2025, in early January and February, we were lucky enough to have the opportunity to visit that remote place on Earth. And it was a fantastic voyage. And we took the vessel as further south as she ever been before, which was really a bonus. So today I'm going to be sharing with you some of the activities and why we went there. And it's the perfect audience, the Antarctic audience, to present this experience to you. A little bit of motivation, and this is. So we go to Antarctica every 2 years, and many other institutions and people doing Antarctic science, and not only Antarctic science, but global science, trying to understand how this Earth is changing. We are very focused on trying to understand how the ocean is changing, because the ocean is maybe I'm a little bit biased because I'm an oceanographer, but it's one of the main drivers of how the climate is going these days. And particularly the Southern Ocean is changing quite a lot, and not for many decades, but maybe in the last decade has been changing quite dramatically. This figure here that you see on the right-hand side, it shows how the global ocean is changing, and if you focus on the Pacific, which is just the right wing on the screen, it will show you that the global temperatures have been increasing. The Southern Ocean has been historically the coolest ocean. It brings water from the abyssal ocean, just cooling the surface. And now we are finding that temperatures in the upper 300 meters of the ocean closer to Antarctica are actually warming up. And that's potentially driving the recent changes that we have seen in sea ice, for example, seeing less sea ice every summer. The Southern Ocean closer to Antarctica is still producing cool water that cascades down from the continental shelf and then ventilates the Southern Ocean and then moves away and keeps basically the global system as it is. But if this changes, you can imagine that we will have immense consequences for the climate and also the ecosystems that depends on the ocean, and eventually societies that rely on ocean for food and everything else. And in the left-hand side, you see this is the global ocean heat content, and as this recent paper has been just result from this paper has been published, maybe I think it's early January. It's showing that 2024 has been the hottest year in terms of global ocean heat content. So basically, researchers like me and Craig and others and the Antarctic Science Platform, and we are really worried about the consequences of these increasing temperatures and heat content. And that's why we go every year or every 2 years when we have the opportunity, just to make sure we understand the impact of this change on everything else, such as ecosystems and particularly ice, how this ice will melt, and what will be the implications for global sea level rise, etc. But despite this system being quite open for us, for example, the map on the left, you see this is sea ice concentration, and everything that is light blue is just water. So it was really easy for us to just move across the Southern Ocean and reach the continental shelf because it was ice-free. However, there are some parts in this system that they still have some sea ice, especially the coastal regions, which is the areas that most of the important ecosystems reside. So we have some challenges navigating to sea ice in some opportunities, but most of the time we were really lucky and we had excellent weather, which allowed us to do all our planned operations. So the main activities that we planned for this voyage was just to look at these benthic ecosystems. We visit them before. I mean, when I say we scientists, we have been visiting those sites before. We want to see the impacts of changes in these benthic ecosystems, which are the ones that live closer to the seafloor. We did some hydrographic surveys. We went all the way to the Rosa shelf front to collect some instrumentation, what that we left there a year ago. And we also did some studies on fisheries, particularly focusing on tools such as eDNA and monitoring zooplankton distribution. And also we did atmospheric experiment, which here Hannah was in charge of looking after those samples, and Holly probably will talk later about the connection of the aerosols that she's been monitoring in the ocean with the ice core one. We were also really lucky. We have the best science team. This is us. This is a picture of us, and it was a good mix of early career scientists, such as 45% of the science team was in the early career stages, and also students. And it's just a great opportunity to have that experience when you're early in your career. Just go to Antarctica. Some of the people in the team, they went on a ship for the first time. And it was to Antarctica for 6 weeks. So it was quite important milestone for them. But also a mix of really experienced science support team and scientists as well. So it was quite mixed, and everyone was amazing, really. And probably the success of this voyage, it was because of the amazing team that we had. So as you can see in this table, we have people supporting instrumentation, the technology team, which without them, we couldn't perform any of the measurements. They are the experts and we rely a lot on them. And then we have the benthic team, which was quite big. They were the ones focusing on ecosystems, and the fisheries and zooplankton team, they were looking at the distribution of species from Wellington all the way to the Ross Sea. And then we have the atmospheric team with Hannah, but with support from Dan, from Holly, and everyone on board. And so this was my first experience planning a voyage like that. So we had a set of milestones to do, and then we plan a route. So every magenta diamond that you see there, these are the pivotal points. These are the points where we have instrumentation that we either deploy before and we need to get them out of the water. So we sort of had an idea where to go and where we wanted to go to recover those instrumentations. But then the factor of weather and other things can break, instrumentations can break, you need to come up with a plan B. So that was a little bit of uncertainty, but so this is what we planned, and this is what we ended up doing. So this look that you see here is a little bit more convoluted, but essentially we were so lucky with the weather and the instruments that we had and the machinery that we used to collect those observations that we planned to do worked really well. So we actually achieved a little bit more of what we planned. For example, we went to places like we didn't think we would go. For example, Wood Bay and Franklin Island, which is for the south. We went all the way to the Rosa shelf front, which was a big unknown. If ice was present, the TANGAROA vessel is not an icebreaker, it's just ice strengthened. And so we had to sort of navigate the sea ice as best as we could. But because we didn't have sea ice, it was a really nice trip for the south, which was really, really good. We spent a few days in front of the ice shelf recovering moorings, and it was quite an experience, not only for us, but also for the crew of TANGAROA, because as I mentioned before, that was the first time that the vessel went as far south as it did. So it was quite a milestone for everyone on board. So I cherish that experience. I think these are the bonus things that make the experience more enjoyable, and yeah, it's just something really special to go in that part of the globe. So one of the activities, as I mentioned before, was to recover moorings. There were a set of moorings that we have placed in strategic regions in the Ross Sea. For example, the Western Ross Sea. This is the place where all of the dense water that forms at the surface, so it cools down, sea ice forms. The salt is not retained in the sea ice, but it's just rejected as a brine, and then the water becomes really, really dense, sinks, and exceeds the Ross Sea continental shelf. And when it forms, it absorbs all of the gases that are in contact with the surface, because these water mass or dense water masses form at the surface. And then it ventilates with that oxygen and all of the nutrients that captures. It just sinks, moves away, and transport that to the Southern Ocean, and then it moves and populates the global, all of the global basins. So having those moorings there and trying to understand how these salinity signals and oxygen and temperature changes is quite important. So we kept these moorings. We have been keeping these moorings for a few years now. And so we recovered them and then redeployed them. So this was one of the activities that we had. It was a multidisciplinary activity, because we also collected water samples on the way. And this is also collaborating with people not only from New Zealand, but from the UK. Another important activity that Svenja Hafter from NIWA, she's trying to keep going, is trying to understand the distribution of zooplankton species as we cross ocean boundaries or frontal systems. The distribution changes, but with these changes in temperature and salinity, there is even further change. So we are trying to keep that long time series of these different species going, so we understand the impacts of these temperature changes that we mentioned before. So she was collecting all kinds of creatures that I never seen before. But yeah, really intensive work, because she started doing this since we left Wellington and never stopped until we came back. So another instrumentation that is key in collecting not only physical parameters, but also biogeochemicals, such as, for example, chlorophyll and oxygen and other parameters, is a glider. And we had Jasmine McInerney piloting a glider mission that we planned for this voyage. So basically, at the start point, as you see in this map, that was in our way on our road south. We left the glider there, and we left the glider just glide for a few days, or actually maybe weeks. And we recovered the glider on the way back at the point that is noted there as last. And the pathway of the glider was through a trough. That's the Drygalski trough. And we understand from previous measurements that in the troughs is where heat exchange happens with the offshore part of the ocean. So it's quite important to understand how not only temperature and salinity are changing in those places, but also what's happening with chlorophyll and oxygen, and how these properties are changing. So the glider, we hope it will provide a really nice data set that we can further investigate and provide some information of what's going on in these really key places in the Ross Sea. As I mentioned before, the benthic team was one of the biggest teams in terms of people, and they, as you can see in these figures here, in these photos, they had quite a of varied jobs since the moment they observed these benthic ecosystems until the moment they actually sampled this ecosystem. So basically what the protocol for sampling consisted in going to a particular place. We will know the bathymetry of the place, so we deploy a camera system, and then we will tow that camera system for a few kilometers, and then we'll be able to observe all the types of species in those areas. I was quite shocked to see starfish. I didn't know that starfish were so abundant in the Ross Sea. I thought it was more like a Caribbean and tropical thing, but no, obviously no. There's a lot of them and a lot of species. And so they were calling the different species and sponges and everything that they observed. And then we went back to the location of sampling, and we will just dredge in that area and collect the actual species. And we were really careful looking after vulnerable marine ecosystems. We didn't sample in places that were, for example, black corals or other species that are protected. So it was quite a varied activity and beautiful. Really, looking at those images at the seafloor is just amazing. Yeah, you couldn't believe those species were surviving in such a hostile environment. And probably this is also a reason why we need to keep an eye on them, and weather changes in heat and all the things that are changing in the Ross Sea are going to impact these communities. And the idea is just to create these, just to go to different sites and maybe just establish them as a long-term monitoring sentinel sites. And this is what the benthic thing was after. Highlight of the trip was to go, as I mentioned before, as far south as we could go, and to recover key moorings. And these are key moorings because they are just at the front of the ice shelf. So imagine the ice shelf, and just beneath what you can see is just a cavity. So it's ocean in there, which is in contact with the land, and is what eventually, if that temperature will increase in the cavity, it will melt the sea ice in that region, and it will create really huge impact on how much water can come out from Antarctica, and affecting sea level rise, affecting circulation, because it will affect how the ocean will change the layering system, and how the ocean moves, how fast it moves, how slow. So recovering those moorings was a quite a milestone as well. We recovered 4 of them and redeploy 1. So at the moment there is 1 in the water at that location, and hopefully that will be recovered maybe next year or the year after. And this is a good dataset that I think Craig will and others in the team will really enjoy working with. Another type of instrumentation that is part of a much bigger system that we in New Zealand have is Argo floats. We, as a New Zealand entity or country, we have a long-standing relationship with the Argo program, but this was a unique opportunity to connect to the biogeochemical Argo program. So these are floats that, as they move up and down the water column, they collect temperature and salinity properties of the seawater. But these particular floats, they have more sensors. They have an oxygen sensor, and also they can detect chlorophyll changes. And the idea with changes in sea ice, we don't understand how the ocean near the ice shelf is going to change in terms of not only temperature, but also all those ecosystems that we are worried about. We don't know how much, for example, how much phytoplankton is going to be there, whether less sea ice or more sea ice will affect the cycling of oxygen, and how these properties are going to move with circulation. So now with these 2 instrumentations that we just deployed, we're going to be able to infer how the ocean more as a whole is changing, not only the circulation, but what are the impacts on the ecosystems. And these flows are currently under ice, so we will hear hopefully of them in maybe October or November later this year, where sea ice melts, so the float can come up to the surface and communicate with the satellite, because this is how they transmit the information. They just in situ measurements that connect to the satellite and then back to land, so we can grab those data points and analyze them. Other really key activity was just to try to understand interactions between higher trophic levels, and this is more focused on fisheries. We were also having a team led by Alina Sherin. She's from India, from the Center for Marine Living Resources and Ecology, and there is a partnership that trying to understand how these changes in ocean properties will affect the distribution of fish, and they are trying to use really novel techniques, for example, acoustics combined with eDNA barcoding, metabarcoding, and zooplankton, just to understand how this distribution of fish will change in the future. So they have collected a lot of information, which is actually filtered water, and they can use these techniques to track back whether they can find that species in that place or not. So this is, I'm looking forward to this research. I think there are a lot of samples that we collected and hopefully will reveal really interesting results. This is another addition to this eDNA technique led by Gerjan Julian and Miles Lamar from Ottawa, but also people from NIWA and Italy. So there was a lot of people from different places trying to understand how to use also eDNA techniques to look at how population genetics distribution is changing with climate change and ocean change. And also here, a picture of Hannah, but you have them here in person. She was sampling for Holly Winton in a sort of ocean atmosphere experiment. This is just to characterize aerosols. And yeah, I think there is a link to phytoplankton in the Southern Ocean, and then they can use observations that we collect on the way. So this is the station that was mounted on the bow of the ship, and they can collect observations just as we go, but also complementing with some water sampling that we did. And the idea is just to understand how phytoplankton is changing in the Southern Ocean, and yeah, how it's linked to atmospheric as well in climate. So to summarize, we had really an amazing voyage. I'm still smiling about it. And yeah, I think, yeah, you when you go to Antarctica, I think you prepare for the worst, and not the worst in terms of everything is going to fail, but you know it's challenging. So you prepare for those challenges. And when you come back, having done so many sampling stations and collecting everything that you could, and also have a great team, it's just you can't ask for more. We had also really good engagement with media. Craig was really good at communicating our activities in a matter that was super engaging, and I think this is super important for transmitting what we do to more general audience. So that was really great, and yeah, we were really pleased with the engagement from people. And yeah, again, best team that we could have, with a mix of having a good time. I think it's really important also to not only focus on the science, but also provide a good experience in terms of balance and having a good time, but also working really hard. So we try to make that happen, that we have some good times, times to relax and getting to know each other, but also then working long shifts and trying to do good science. Special thanks to the Antarctic Science Platform, NIWA. I don't want to forget anyone, but I just want to mention also that the crew of Tangaroa is, we couldn't have done that without them. They've done so many voyages. Our voyage was the number 16, and some of the crew members, they were doing the 15th voyage to Antarctica. So they know exactly what to do, and they're super supportive, and without a teamwork, nothing is really possible. So yeah, and that's me. So thank you. And if you have any questions, I'm here.
Our next two speakers are actually Wellington locals, but for various reasons, they are not here in person with us tonight. I know that Jacqui, who's our next speaker, has already given one talk today to a crowd at Otago University. So So yeah, she's having a busy day. So Jacqui is a marine ecologist who has recently completed her PhD, so now Dr. Jax, and she's been joining me on my platelet ice work, which I've probably bored you all to death with over the last 3 or so years. But Jacqui's got a different perspective and certainly a different way of talking about the work that we're doing. So I shall hand you over. Thanks, Jacqui.
Kia ora, I'm Jacqui. Thank you for the intro, Natalie. I am going to be talking to you a little bit about platelet ice, but a little bit more as a habitat for one of my favourite wee things, which is microalgae. So we headed down in end of 2024 with the big platelet crew down for a sea ice camp, and I'm just going to talk you through a few of the things that we did. So we ended up camping out here near out off from Scott Base on the sea ice, and we were mainly focusing on that platelet ice that Natalie has talked about before. So you're looking at this here. The platelet ice on your right, I think, is these nice beautiful billows that form underneath sea ice, and you can see here a platelet crystal, which, much like the name suggests, it's a plate-like shaped piece of ice. That this one's about the size of your hand, and so these form not everywhere, but they rely on the existence of an ice shelf nearby, which we do have there in McMurdo Sound, and this creates super cooled ice shelf water that comes out from under that ice shelf, and in that we've got these lovely little frazzle crystals, and they, as they rise to the surface, grow to form these plates of platelet ice and then come to rest on the bottom of the sea ice. So you can see there, we've got our snow on the top, we've got our fast ice or sea ice there, and then we have a beautiful platelet layer accumulation underneath that, which has a whole lot more space in it for things like microalgae compared to sea ice. So I've mentioned microalgae a couple of times, and I'll actually introduce the heroes of our story here. So you're looking at a diverse range of microalgae from actually within McMurdo. So these are some photos that I took through the microscope from our 2022 season. But these little heroes have been mentioned a few times before, but they take the sunlight and create energy in their cells. So they provide a whole lot of energy and nutrients to all of the other creatures in that Antarctic ecosystem. Now, all of these microalgae are not built the same. You can kind of divide them into these groups, which they play slightly different roles in their communities, as well as providing slightly different, you could say, like nutrients to the things that graze on them, like I said before. So we headed down with a crack team of scientists. There was 11 of us, and we have a combination of skills ranging from physicists to oceanographers to engineers to ecologists and biologists and everything in between. So lots of skills and lots of different lenses to look at these things through. And we headed out onto the sea ice, and this was our home for about 3.5 weeks. So we've got lots of containers here, and these are a combination of living quarters for kitchen or sleeping, laboratories, so for our biology work as well as oceanography, and then things like generators, and we've got our lovely tent set up there and the Haglin all parked up ready to go on an adventure. So because there were so many of us with such a broad set of skills, we had a whole lot of amazing equipment down with us that meant we could look at the platelet layer and sea ice in many different ways. So there was a series of EM surveys, so they were looking at the thickness of the platelet layer, and one of the master's students, Lizzie, along with Greg, were looking at these and doing these big transects. We had Lee Tate from NIWA come down and do some ROV surveys under the platelet layer, as well as some just manual snow, sea ice and sub-ice platelet layer measurements. Of course, the famous platelet layer cores and then some new pieces of kit to look at the conductivity within that sub-ice platelet layer to help feed back, hopefully, into the EM survey work, and then also some light sensors to see what's going on underneath the ice and above the ice in regards to the light that's getting through it. So I'm just kind of focus on two of these things, so our platelet layer cores and then those manual measurements, because much like in 2022, the sea ice in McMurdo Sound in 2024 experienced a series of storms early on and in the winter, which meant that there was kind of there was some slightly later formation of sea ice in the majority of the sound. And so we looked at kind of the difference in properties between these, what we call March sea ice versus August sea ice. And so here, based on those measurements that we took, so we're looking first here at the snow depth. So on that sea ice that formed a whole lot earlier in March, we were seeing some quite deep snow compared to that sea ice that formed a lot later in August. So the difference is about 26 to 30 centimetres versus a 2 to 6 centimetre. So obviously the thinner ice was a lot easier to work on whenever we had to go and dig holes, which I know we all love digging snow, but sometimes it gets a bit much. And then similarly, there were big differences in the thickness of the sea ice. Of course, that's expected. The sea ice has been there for longer. So the March sea ice was just under a metre thicker than that August sea ice. And then, of course, back to that lovely platelet layer, we again saw some quite big differences between these two platelet layers. So we ended up with almost 4 times the depth of platelet layer in some areas on that older ice. And this, of course, makes sense again, because if the sea ice isn't there, there's nothing for the platelets to come and rest against, and you don't form that platelet layer. We also were able to get some measurements of how those platelet layers were different physically. So what you're looking at here is from the top of the figure to the bottom is from the bottom of the sea ice down through the platelet layer, and along the bottom is the percent of water. So what we're talking about is how much of the platelet layer is actually ice crystals versus how much of it is actually water. And so you can see from that older ice, there's a whole lot more ice crystals in those shallower layers compared to the amount of water. And then in the August ice, there's a lot more water, a lot shallower, and that pretty quickly, as you go through that platelet layer, ends up mostly water. So what does all of that have to do with the platelet layer as kind of a habitat? Well, when you look at this, you might notice something slightly different about these two platelet layers as well. A little bit of something to do with the coloration potentially, and that is, of course, the wee champions I've brought up a few times now, our microalgae. So when we think about the differences in those two platelet layers that we were seeing in 2024, which was similar to differences we saw in 2022, you've got a whole lot more space vertically through the depth of that platelet layer for the microalgae to live. So there were similar amounts of microalgae in the entire depth of this platelet layer. However, it's kind of the equivalent of living in a really high density kind of apartment building versus out on a lifestyle block, right? You've just got so much more space to move. And then add that to what we're talking about here with a bit more water between those platelet crystals, potentially more surface area because the crystals have more space between them, then there's just a bit more space in general for those microalgae to kind of do their thing. So on top of all of this, you think about those changes that we're seeing from that older ice to that newer ice, and overwhelmingly, essentially, you end up with thinner snow, thinner sea ice, and thinner platelet ice. And that gives you a bit more light that gets through all of these layers, right? And microalgae love light. That's what they create energy from. So we decided to see how that light in sea ice of the same depth and platelet layer of the same depth was actually affecting the microalgal communities, how much microalgae was in these platelet layers, as well as the composition of these communities. And what you see here in this picture is the efforts of 4 people over the space of a 9-hour workday with a whole lot of snow shoveling. And really it appears as though we've barely made a dent, aside from the clear snow, which is our low snow, high light experiment treatment, which we moved all of that snow to a big 10 by 10 metre square behind that, which was our high snow. And so that's 10 centimetres of snow depth. And then we left a whole lot of snow for our ambient conditions, and we took some of these sub-ice platelet cores that Natalie's talked about at different time intervals to see what was happening in these communities. Now, we took all of these back to our lovely lab on the ice, and immediately we're seeing some differences through those cores just based on the coloration of our filters here. So you can all these different algae also produce slightly different pigments, so this is potentially indicating that there's just visually different microalgae in these different layers through the platelet ice. And then we also, this is actually a photo from 2022, because I couldn't convince all of the physicists and oceanographers to pose for another photo with a microscope. That was just asking too much. I'd managed that once. But we did get people looking down the microscope again and getting enthusiastic about what microalgae we were seeing. So just some preliminary data, because I got really excited and couldn't help myself. But what you're looking at here is, again, the top of the figure is the bottom of the sea ice, and we're going down through the platelet layer, and then across is biomass, or how much algae. And then we've got our ambient snow load in grey, our low snow loads, that bare ice, in green, and then our high snow load in red. And without getting into the details of it, you can see that there are changes happening across these time periods. We've got to dive a bit deeper into that, but this is pretty hard to see with it when you can see that the ambient's quite different. So just to simplify that, here we've got our 0 represents that ambient condition, and then these are the percent change of that biomass compared to the ambient. So you can see after 1 day of being in that condition, there was a big change in biomass in both of the high and low treatments, and that slowly over the duration of 10 days worked its way back towards matching those ambient conditions. So there's still lots of analysis we've got to do to understand more of what's going on here, but we can safely say that something's going on with the microalgae when you move snow around and change the light that they're being exposed to. So on that, and that's kind of the summary of what we think is happening so far. But essentially, I'm going to leave it there. Just say thank you. Of course, this work is not possible with a whole lot of people and a whole lot of support. So it is not just me. It is a culmination of many, many people, including Natalie. So thank you. That is all from me.
Awesome. Thank you, Jacqui. And it's amazing having biologists on your team, especially one as prolific as Jacqui. In both talks that she's given today, she's presented data that I hadn't seen, and I'm seeing her every day. So that's how fast she's producing data right now. Peter's asking about the song that you sang on national radio.
Oh, yes. Unfortunately, I don't have a guitar with me right now, or I could have just done a rendition for you instead. But yeah, that was inspired by my love for these little guys. It's if you ever bring a guitar to my office, I'm happy to sing it for you, you know.
Claire Kincannon's released an article on RNZ which closes with Jacqui's phytoplankton song. So you could look it up and listen to it. All right. Our third speaker tonight is Holly Winton. She studies ice cores, which of course can be used to look at sort of climate histories, but quite a nice connection with Jacqui's talk is that at the moment, Holly is focusing on what ice cores can tell you about the productivity of the ocean. So take it away, Holly.
Tēnā koutou katoa, mai I ki te iho kei te pai o te tātou hui huinga tēnā tātou katoa. Hello everyone, thank you Natalie for the very warm welcome. So thank you very much Jacqui also for setting us up talking about microalgae. So phytoplankton, they're these tiny marine plants, but they have a massive impact on the global climate. They do this through the carbon cycle, but they also emit biogenic aerosol to the atmosphere that seeds clouds and reflects solar radiation. So despite their importance, we actually have very little information about how and why they've varied in the past, which limits our ability to anticipate the future. In this schematic, you can see how both marine life in the open ocean and undersea ice impacts climate-relevant aerosol in the very pristine atmosphere over Antarctica and the Southern Ocean. So changing sea ice conditions not only impacts the habitat of these organisms, but also the composition of the atmosphere and processes related to cloud seeding and radiation. Luckily, ice cores record a history of these marine and biogenic emissions that allows us to extend the relatively short record we have of phytoplankton and sea ice to understand the relationships between the two. So over the last 2 seasons, our event captured information about biogenic aerosols, and we drilled shallow ice cores to understand the history of phytoplankton climate in the Ross Sea region. So our team's using an integrated approach to understand how changing sea ice conditions impacted primary production in the Ross Sea marine protected area over the last 200 years. So to do that, we're using a combination of real-time aerosol data collected from ships and also from ice core sites, and combining that with a longer-term perspective of ice core biomarkers of fatty acids, which will provide us information about of the phytoplankton. And we're using this information to constrain biogeochemical modelling to assess the sensitivity of the phytoplankton to changing sea ice conditions over the past 200 years. So our team were very interested in going to Terra Nova Bay. This area here, it's a biological hotspot in summer, and this polynia is kept open by catabatics draining the East Antarctic Plateau. And we identified 2 potential ice core sites that satisfied a very long list of criteria to preserve biogenic aerosol in the region. So the first was up here, south of Upper Priestley Glacier on the East Antarctic Plateau. It's about 2,000 metres above sea level, 100 kilometres from the coast, and it's very much plateau-like conditions. And this is where we went in 2023 and 2024 season. This last season, we went to Thurn Promontory, also 2,000 metres above the coast on a coastal ice dome, much closer to the coast. Here's a picture of the ice dome from colleagues at Montana in the States. You can see the lighter below is the bedrock, and the ice is the darker on the top. And so we went to this site for about 3 weeks. And the other important point to note here is that this dome is surrounded by 2 valley glaciers. On the north is Upper Priestley and the Reeves on the south, and we'll come to why that positioning influenced our experience at Thurn Promontory. And so this is a picture of this shallow coastal dome from helicopter when we were coming in to land. And here's a short flyover from the helicopter of our site. That was a relatively small camp. So we had 4 on our team. And so this is, we had two sites on Thurn Promontory. This was our camp or our living area, and it was actually separated by a 500-metre flagged route to our science site. And that was because we wanted to avoid contamination of our camp activities with the measurements we were making. So we were collecting aerosols and drilling shallow ice cores, and we didn't want our camp activities to contaminate the very low concentrations in the samples we were collecting. So this was our science site. I'm not sure if you can see 2 people there in white clean suits waving. That's where we had all our instrumentation and collected all our samples. So we had a number of objectives. The first was to drill a series of shallow ice cores, and we did this using a Kovacs drill. It's a rather simple system. And here's Emma just testing out the drill. It's a 1 metre barrel, so we can recover 1 metre cores at each run. And for the first few metres, we can do this just manually with a T-bar. And you can see this picture in the middle with these 1 metre extension rods. So after we've drilled a metre, we add on an extension rod for the next metre. And then as we get a bit deeper, we need a little bit of assistance. So we use a power drill and a hoist system to help us recover those ice cores. We then process them into 1 metre length bags and transport them back to New Zealand in purpose ice core boxes. And very happy to say they've just arrived in Christchurch. So the second objective was to collect daily surface snow samples and dig and sample a high-resolution snow pit. So this is Emma and I in our clean suits in the snow pit, and we wear these clean suits because we want to avoid contaminating the samples. And you can see in the background this very impressive lenticular cloud. So these are a sign of mountain waves. They typically occur downwind from mountains, and there's quite a good sign of gusty and very windy conditions on the ground. So that gives you a bit of an idea of the sort of conditions we were working in. This is a picture of the backlit stratigraphy of the snow pit. So we dig down onto one side and we dig behind it, cover it up, and then the light shines through so we can sort of see the layers and stratigraphy of the pit. What you might see is some of these wind features that are imprinted in the snow pit or sastrugi. Then when we look at the surface, you can see the site was very much impacted by blowing snow and strong winds with the sastrugi. Some of these were 20 or 30 centimetres high. And I'm just contrasting this to the more plateau-like site up at Priestley Glacier. This was our 2 metre snow pit there. And you can see in the backlit stratigraphy that we had much more horizontal laminar layers, which are more suitable for ice coring. They help us preserve a continuous record of snowfall and aerosols. So we collected daily surface snow samples, and those were to relate to our next objective, which is an air snow transfer study. So we measured the chemicals and the biomarkers in the ice core, but we also want to understand what's in the air, the sources they come from, and how these impurities are preserved in the ice core, or how they're archived there. So over the 3 weeks we were there, we collected aerosol filters and measured real-time aerosols and meteorology. So to collect our aerosols, we need very large volume samples because the air is so clean, so pristine. So we use a high volume aerosol sampler, and that has a PM10 side selective inlet attached to the top. So it's we're collecting aerosols less than 10 microns on filters. We also collected other high resolution aerosol samples every day. These are low volume, and we can measure trace elements and black carbon on them. On the top here is our sonic anemometer or weather station, so we were able to get weather data at the site. We also measured real-time aerosols, so the number of them and the size. We had a snow stake to understand how much accumulation was occurring while we were there. And then inside this tent was our aerosol lab, so that's where we put all our instruments. They were sheltered away from the conditions. And we also had a clean area where we could change over our filters it was designated areas to avoid contamination. So this was some of the conditions we experienced when we were there. Temperatures ranged between -10 and -22 degrees, so it was about 10 degrees warmer than the Upper Priestley site where we were last year. But we had very strong winds. We had wind gusts up to 115 knots. We had a couple of good days working, and then a few days that we were confined to tents. So when we went to the site, we had anticipated we would be above and to the side of the catabatics, but in actual fact, it was very much influenced by the catabatics. Just some preliminary aerosol data. So this is a time series of the number of aerosols or the number of particles in the air and their size. And while we were there, it gets super interesting conditions. All the winds blew from the plateau. The aerosols were very small, less than 1 micron, and there were hardly any of them. In contrast to Upper Priestley, where we went the previous year, we actually had 2 very interesting events that occurred when we were in the field. We had intrusions of marine air masses. So when we get much higher concentrations and larger particle sizes, and we link these with modelled air mass back trajectories and the chemistry, and we can fingerprint them to the marine region from Terra Nova Bay, which was a very good sign. It's the information we were hoping to capture. Then our last objective, we wanted to understand how thick the ice was and get an idea of the stratigraphy. Our longer term goal was to go back to one of the 2 sites and drill a deeper core. And so we used ground penetrating radar to do that. This is Moraine Thornton. He had 4 different antennas ranging from 25 to 400 megahertz. And he basically traversed the entire, this is a picture of Moraine and our field trainer with the GPR dragging behind him. And he basically traversed the entire safe zone of thermometry, collecting these measurements. And this is an example of a radargram at thermometry. And so on the bottom is the bedrock, and on the top is the snow and ice. We measured, the deepest part that we measured was about 200 metres, which was the thickness we were sort of hoping to get. And on the right is a close-up, this close-up of the stratigraphy. It's for top 4 metres, and you can see it's sort of very wavy and reflects what we see at the surface and also in the snow pit. We contrast that to the more plateau-like site at Upper Priestley Glacier. This is the top 16 metres, and we see much more sort of horizontal laminar layers, which this site is definitely standing out as the site we want to go to in terms of the glaciology, the marine air masses that we receive at the site, and the chemistry that we're measuring in the ice core. So then Hannah Ishii measured a lot of these same atmospheric variables at sea on the TANGAROA voyage. She was very busy and collected hundreds and hundreds of different samples for biomarkers and biogeochemistry in the atmosphere and in the seawater, because we're of course interested in the source and understanding the ocean-atmosphere exchange of the biomarkers and impurities we measure in the ice core. So massive thanks to our field trainers, Pepper Cook and Glenn Smith and Antarctic New Zealand for supporting this work. Thanks to IBR, the helicopter from Southern Lakes, and also Ken Borrick, pilots for flying our ice cores on a cold deck, not the most pleasant experience. And also to PNRA, the Italian programmer Mario Zucchelli, for hosting us. We were staged out of the Italian station for our put in and pull out, as was the Kiwi helicopter, and we had very amazing hospitality, great food. The Italians were able to provide us with weather forecasts every day at thermometry, and managed to find space in the Beyond Epica freezer for our ice cores while we transited through. Tēnā tātou katoa.
In the ice cores, did you ever see traces of smoke from Australian bushfires of 2 or 3 years ago?
Did you hear that one?
Great question. It's something we're definitely interested in measuring because our ice course, of course, will capture that very large Australian bushfire event. So it's something hopefully we'll be able to answer when we have a bit more of our chemistry data.
Do you know what your accumulation rate is at that site, Holly?
Yes, so at the plateau site, Upper Priestley, it's relatively low accumulation, between 7 and 10 centimetres of water equivalent a year. And where we were this year, it was higher. So that was one of the goals of going to a more coastal site. We'd get a higher accumulation rate and more detailed record. It was around 15 centimetres per year.
Right. All right, lovely. Thank you very much, Holly. And I'll just move to our final speaker, Gary Wilson, who is joining us. Oh, well, I'm not exactly sure where he is, but he's the Deputy Vice-Chancellor for Research at Waikato University. Probably doesn't need a great deal of introduction. Most people here probably know Gary. But what I'm most impressed by Gary at the moment is that despite all of his various governance roles, he manages to keep his hands dirty in the research. So that's a point for me to learn from as I'm feeling like I'm losing contact with my research. So I'm looking forward to hearing from you, Gary.
Yeah, thanks, Natalie. Kia ora tātou. I am actually in Hamilton, and I'm very pleased that that you include Hamilton in the Wellington branch of the Antarctic Society. Although I would point out we do have a functioning water and sewage system here, so maybe we can share some of that with you. Anyway, so yes, I'm just going to take a few minutes to talk to you tonight about a project that I have kept my hands dirty with for a few years now. It's a joint project between the Italian program and the New Zealand program, and so we've been working for more than 5 years now in the Taylor Valley, a little bit in the Wright Valley, measuring soil gas emission. And it was an interesting project, and it still is, it's still going. And it was interesting because we kind of expected to have low amounts of soil gas emission, and I guess the amounts are low compared to the Arctic, but they're still significant and growing. So that's what we've been getting involved with. And as you can see, a cast of quite a few people involved here. A lot of students, people on the geophysics side, people on the geochemistry side. So a lot of effort going into that. I guess what's motivated us is trying to learn what the difference is here between the sort of accountant's view of carbon zero, which is trying to get our emissions back to zero, and realising that actually we've already got to the point of warming of the planet, that the Earth is now in a positive feedback mode and starting to release a lot of its CO2 reserves back into the atmosphere. And of course, the permafrost is one of those large CO2 reservoirs. The Arctic permafrost alone is big enough that it could put the same amount of CO2 into the atmosphere as we've managed in the whole of since the beginning of the Industrial Revolution. So it's a large amount of carbon. But we didn't know what the number was for Antarctica. It was kind of zero in the calculations, and that was simply because we didn't know. So what I'm interested in, and we're interested in, is getting to the bottom of actually how much beyond carbon zero is that going to push us? And so here we go. There's the number for you, 17 gigatons of carbon in the Arctic permafrost in the store. As I said, that similar order of total emissions since the beginning of the Industrial Revolution. And the current release rates are about 600 to 800 megatons per year. And that's expected to rise to almost 100 gigatons per year by 2300. So it's not going in the right direction. And the current anthropogenic emissions are only 37 gigatons. So it's going to outstrip what we're able to do as humans, although one would argue we've done that as well. So that's kind of the driver. But of course, as I said, we thought the CO2 would be low in the Antarctic because it's a carbon-limited system. Well, it turns out that, yes, there's little organic carbon in the permafrost, but the system isn't carbon-limited. The microorganisms, as you can see there with the cryptoendolithic microorganisms there, something that Imre Friedman worked on a number of years back, they're able to reuse carbon and fix inorganic carbon. And the carbon is plentiful if you look at inorganic carbon supply in the transantarctic mountains and the dry valleys. So it turns out actually the system's not carbon limited, but we still don't know the CO2 content of the permafrost. And that was the objective that we started out with. But as you'll see, we moved a little bit along the way. So we conducted a soil gas survey of the Taylor Valley just to get a number and try and build a little map of what the soil gas emission was. And you can see there with the yellow dots on the right-hand side, that's the sampling that we carried out in our first season of measurements. The samples are collected from the top of the permafrost, so the bottom of the active soil layer. So it's just trying to measure what's actually being released from the permafrost as opposed to being produced in the soil itself. And we made the analyses in Antarctica. And there's the result. It's the gases we've got there are CO2 on the top right, methane on the top left, helium on the bottom left. And helium's an interesting one because where you've got helium, it's a deeply sourced gas. So indicating that it's not just produced at the surface. And then on the right, bottom right is the flux of CO2 and some of the numbers in the table for those who are interested. But if you put all that together, the conclusion we came to was that, yes, the CO2 was linked to the warmer, wetter areas, but particularly the valley wall margins. And so we came up with this idea of a multi-gas anomalous zone, which is in the pink. I'm not sure what colours you're seeing, but the pinky red. And that's where we've got a concentration, overlapping concentration of CO2, methane, and helium, which is shown in the yellow plus signs. And the CO2 flux is also high with the blue triangle. So it does seem to be along the valley margins. And so that suggested that actually probably the source was it not so much the permafrost, but it was the valley wall faults in the permafrost, allowing the CO2 to come from depth. And so just this next slide before I go on to perhaps the origin then. So the number, there were previous measurements in the dry valleys, and you see those running along there. They're reasonably low, but with this comprehensive survey, the 2019-20 number was pretty high, probably 5 or 6 times what had been previously measured. So that was a bit concerning for us, and we've continued to see a high number. So looking at that, we thought, well, what's the option for the origins? Biogenic bacteria in the soil and in the permafrost, still a possible contributor where things are warm and things can increase, but there's still relatively low amounts in the permafrost. It could be icebound, but, we're not really starting to melt the permafrost like we are in the Antarctic, like we are in the Arctic. Maybe biogenic accumulating beneath the permafrost cap. That's not particularly likely as biogenic processes are pretty slow at depth. And then physical, transported at depth. And there's recent evidence from Jill McCookie's work to show that there's brine flow at depth in the Taylor Valley. And if that does come out from the East Antarctic ice sheet, there's potentially an infinite source. But we don't know that the flow rate would change with warming. It may not be affected by warming until we really warm it up. So this is just a snapshot of the brine, the aeroresistivity published by McCookie, 2014. And you can see in the blue there, that's the brine at depth, that's the groundwater. And then the reds and yellows and purples are the ice and permafrost. So the hypothesis from Jill and her team was that the water was flowing out from under the Taylor Glacier all the way through Lake Bonny, Lake Hoare, Lake Frixell, and into McMurdo Sound. And we do know there are groundwater seeps in McMurdo Sound. So while it's not all connected up, that was a possible origin. So we got to try to get some detail using some electrical resistivity tomography in the lower parts of the valley where we'd done the gas anomaly survey and ran this little grid of ground-based survey, and we identified something similar. So you can definitely see highly resistant subsurface units. That's the reds and yellows on the top and towards the top right, and that's Coral Ridge in the northeast, the Dry Valley Drilling Project, EVDP 11 site, and then highly conductive subsurface units. So, but that's at 200 to 300 metres depth, even up to 600 metres. You appear to have brine soaked sediments and brine flow in there. But you also have shallow brines looking under Lake Frixell, and even a shallow brine or conductive layer running away from Lake Frixell towards the Commonwealth Glacier. So we definitely see it, and there is evidence that that brine at depth comes up to the surface. It happened in DVDP 10, where they saw the rise of overpressurized brines. That came out quite some time ago. And so it does seem that not only is the brine there, but it's migrating up and down, and it is affecting the permafrost. So maybe with warming, there will be some influence. So as of 2022, we figured there was about 15 tonnes a day released from Lower Taylor Valley. But also we understood the presence of deep origin fluids and shallow permafrost, and we suggested that the gas originated from the subsurface or the overpressurized brine system. So that was where we got to. And so in this season, just gone, we were working on, well, how can we confirm that origin of the gases? And so we had a number of objectives. One was isotopic signature, because we had measured with gas chromatography the gases and the concentrations of the gases, but we hadn't been able to measure the isotopic signature. The other was radiocarbon dating, because it might be that we came up with an age of about 1100 years, which is the kind of modern age of radiocarbon in the McMurdo Sound area. But if we could show that these gases, and of course there's plenty of carbon and CO2 and methane, if we could show that they were much older or radiocarbon dead, then we could show a deep origin. So that was the objective there. We're still working to identify the subsurface structure. So we put out a series of passive microseismometers to capture the ground ice spikes and try and really get some of the structure, permafrost structure, sorted out, which we hadn't really been able to do with the resistivity survey. And then we continued to measure the emissions, so kind of repeat the survey areas. Just a few pictures to show you. On the left-hand side is a simple West Instruments gas flux chamber, and that just stays on the surface and measures the accumulating CO2 and or methane in it, but we don't sample it. And on the middle, that's actually driving one of the probes into depth. This was actually getting in one of the frost cracks to deeper, kind of just between the surface, and it turned out there was plenty of gas once you got even a bit deeper than the surface of the permafrost or the base of the active layer. And then on the right-hand side, that's collecting the gas samples out of the probe. So most of it's done by vacuum, so getting a vacuum system and then just pulling by syringe through the probe and then letting the vacuum draw it into the bottles. So that was the survey. And many samples each day. That's Caitlin Bergquist and Lucy Davidson with some of the many samples collected that day and getting sorted, ready for analysis back at Scott Base. And then back at Scott Base, we had a lab running, both able to just simply with a gas chromatograph measuring gas type and content, and then we also had a Picaro measuring the isotopic signature of the carbon. So we haven't got the results, many of the results yet, but they're quite promising as far as we could tell at this stage. A lot of samples back to Rome now for duplication. Just a quick picture of the seismometers. That's them in the yellow triangles. So just placed to try and get the right wavelength from the ice quakes, and then the white dots, sorry, are the ground resistivity survey that was run in the previous season across that, just the ERT profile. And then it's not a bad place to be. We tend to think of the dry valleys as fairly dry, but we were camped under the Commonwealth Glacier, and a pretty nice camp. And you can see on the main tent there, entirely driven by solar. And even though we had fuel with us, it was only driving the diesel heater. All the rest was powered by solar. And we did get a white Christmas. So you can get a white Christmas in Antarctica. But this was the interesting thing about collecting soil gas samples is even though it's a nice day, you can't do it through snow. So we were forced to stay inside and drink coffee. And pretty nice facility in the weather haven. It's not quite the container camp that Natalie has, but it's still pretty pleasant. And a lot of water. We didn't have to make any water. There's still a lot of meltwater off the front of the glacier. Obviously not coming out from underneath it, but the kind of challenge of being next to the glacier is there's an awful lot of ice fall off the front of this thing. And when it happens in the middle of the night and you're deep in sleep, it's like a train coming through the side of the tent. It's pretty noisy. So it can have its downsides, even though it's a very pretty place to camp. Anyway, that's what we got up to in the last season, and I'll happily entertain any questions if folks have it.
I was curious about the seismometers. So the source is the ice fall and the cracking of the ice?
Yeah, thanks, Warren. No, the source is actually cracking and fracturing in the permafrost mostly, but we probably can use a bit of cracking and fracturing in the glacier itself. Not the ice fall, it's too deep, but the cracks in the ice itself, either the glacier or the frozen ground.
So the cracks in the permafrost would be what, diurnal then?
Well, good question. I don't know the answer to that yet. One might assume if it's due to warming, but I don't absolutely know until we analyse the data. But yes, I guess I'd make the same assumption you're making.
Thanks, Gary. Good talk. Thank you.
I'm curious why you can't take gas measurements through snow. Is it not that you can't do it, but just that it will give you a different result?
Too much water. It's easier to do in the dry system. When you start adding water, it's pretty hard to draw gas through all of the probes. They clog up and ice up pretty quick.
Right. Yeah, that makes sense. We've got a question online from Keith Mandina. Is there any significant sign of the brine flow at the sea front? Is this something to study?
Well, you might be able to answer that, Natalie. There is. We know there are brine seeps in New Harbour, and we know there's biology associated with it. And we also know NIWA have a team who are funded through Marsden to look at that. So, but I haven't heard how their season went yet.
That's Sarah Seabrook that you...
Yes, that's right, Sarah.
Yeah. They found some phenomenal seeps, actually. So, yeah, we might get her in to talk at some point.
I'm Robin Faulkner. I guess I'm not quite as ancient as Peter, but close to it. So it's kind of nice to hear a whole lot of modern science, some modern talks. I mean, I went down by ship, did my PhD dragging magnetometer behind the Navy ship Endeavour, and I think the first one was 58 years ago. So it's a while ago, and so it's quite nice to see a modern ship and all the things that are going on a modern ship. And we were lucky when we went in February that there was relatively ice-free, but then on the trips that were in December, it was pretty well ice-covered, and the Endeavour was actually buckled into the back of one of the US icebreakers and dragged into McMurdo Sound. And that's had its consequences on the way back, when a slow trip would be ka-clonk, 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 with the two propellers both being bent and a rather slow trip back. So it's kind of nice to see the TANGAROA being able to do modern new things. And platelet ice, well, we went down through the ice and it was just ice, you know. I mean, nobody really thought about how thick the ice was or platelets under the ice, let alone all the microbiology that's there. So it's really interesting to see how much it's advanced over the years with respect to that. And then later on, I had the excitement of going on the US ship Tannin, and we did all sorts of stuff there that was much more multidiscipline. And we didn't actually do any air sampling, but we did do some balloon launching. So we had to go at a little bit of air work, not as sophisticated as some of the air work we've heard about today, but just a plain ordinary balloon launched up was kind of fun. And then listening to Gary talk, well, nobody even talked about CO2 50 years ago. It was just not a word that was used, and now we see some really sophisticated CO2 measurements. So it's been a kind of a nice evening to see this contrast between old and new, and to learn so much more about the science that's going on. So thanks to all the speakers. It was multidiscipline. It was very interesting, and thank you very much.